Welcome to Math with Professor V. In this video, we're going to go over how to find the domain of a function, and we're going to look at a wide variety of functions. That way, you'll be a professional anytime you're asked to find the domain of a function. And this is great if you're in pre-calculus, and especially if you're a calculus student and you just need to review some of these concepts. So here's the basic process. Always start off assuming that the domain is all real numbers. So assume that your function, basically, if we're working with the function of one variable, we want to assume all values of x from negative infinity to infinity are going to be part of the domain. Then you work through this list mentally and see if any of the following situations appear, which would lead to us having restrictions on our domain. The first thing to be on the lookout for, in no particular order, are if you have any variables in the denominator. Well, why is this an issue? Because we know that our function is going to be undefined if the denominator is equal to 0. So basically, we want to make sure that the denominator never equals 0. And I'll show you exactly what to do to find the restrictions. So you solve this equation, and this leads to restrictions on x, on the domain. Second scenario to look out for is if you have a radical with an even index. So say you have some radical either in the numerator or denominator or wherever, and the index is this number right here. N is the index. If n is an even number, then you want to make sure that the stuff underneath the radical, the radicand, I'll indicate that with a star, is not negative, because we cannot take even roots of negative quantities and get a real number. So if that happens, what you do is you take the radicand, you take that star, you set it greater than or equal to 0, and you solve. And then that's your domain. I'll show you exactly how to do that. Next thing to be on the lookout for is if you see a logarithm, natural log or log with any sort of base, 10, you name it. If you have log of some quantity, let me not use a star, we'll use a heart this time. Well, logarithms are restricted. This quantity here, this argument, has to be strictly positive, not even equal to 0. So what you're going to do is you're going to set whatever's inside the parentheses, the argument of the logarithm, strictly greater than 0, and solve. And boom, there's your domain. Last thing, doesn't come up too often, but I did want to have a very comprehensive list, is if you see inverse sine or inverse cosine. Sometimes we write it arc sine, arc cosine. And in that case, if you have inverse sine of some quantity, here we'll put a happy face. Well, the happy face has to be between 1 and -1. So think about it this way. The domain of inverse sine or inverse cosine is the range of sine or the range of cosine, which is bounded between -1 and 1. So these are the most common things that are going to come up, and we're going to work through some examples where we practice finding the domain of a function. And these need not exist in isolation, meaning you can have multiple scenarios appear in the same function. Okay? So here we go. Let's practice. Jump right in. Find the domain of each of the following functions. So the first one here, f of x equals x plus 4 over x squared minus 9. So I'm going to assume the domain is all real numbers, and then I mentally just go through this list here. If you need to look at it still right now, that's fine. And I notice we've got variables in the denominator. We have a variable expression down here. No radicals, no logarithms, no inverse trig. What I want to make sure now is that this denominator does not equal 0, because then my function would be undefined. So I do not want x squared minus 9 to equal 0. This cannot happen. That means x squared cannot equal 9. Taking the square root of both sides, that means x cannot equal positive or -3. So those are the only two values that x cannot take on. In all the real numbers, infinitely many of them, everybody else is good, just not 3 or -3. And then how do we write our domain? Not like this. You have two options. You could write it in set builder notation or interval notation, and I'll show you both. I think set builder is more efficient for this particular function. So the domain is all x's. then you draw a vertical line, and when you read it out loud, you say such that. There's some variations on what you can say, but that's usually standard. All x is such that x cannot equal plus or minus 3. Now this is set builder. When you write it this way, we assume everybody else, all other values are a go, just plus and minus 3 are not, okay? How would you write this in interval notation? If you've never done it before, imagining the domain graphed out on a number line is helpful. So this is all real numbers. Here's -3 and here's +3. The domain is everybody except those two values. So if you were to try to write it in interval notation, you would need to write it in 3 separate intervals. This first one goes from -∞ to -3, union -3 to 3, union 3 to infinity. Notice I put parentheses because I don't want to actually include these values, but I want to get dangerously close to them, as close as I can. And then union, I just skipped over -3, take the next piece of the real number line, and then skipping over +3. So this is your other option. So just pay attention whether or not your instructor or the textbook cares which notation you use. This one's called set builder. And then this is interval notation. And I can do both for all the examples, just in case you need the practice, okay? All right, perfect. Let's look at the next example. Here we have g of x equals x plus 4 over x squared plus 9. Very similar to f of x. Only difference is, yes, I see variables in the denominator. It's just we have x squared plus 9 and the other one was x squared minus 9. So again, same thing. When you start off, you say, well, I do not want x squared plus 9 to equal 0, which means I don't want x squared to equal -9. But you know what? That's never going to happen now, is it? You can't square a number, you can't square a real number, and then you get a negative number. This is impossible. So if this is impossible, then that means I have no restrictions. And if there's no restrictions, then I go back to my assumption that the domain was all real numbers. So how would you write that? You have a few options. Probably you've seen, you just write that symbol. That means all real numbers. Other times I'll see x such that x is any real number. That's so much writing though. I don't love it. Interval notation's super fun. You just go -infinity to infinity. That means all real numbers, okay? So take your pick. And I do want to point out something with both of these examples. When we were finding the domain, the numerator had no influence. I didn't even pay a second of attention to that x plus 4 because it's just not important when we're talking about the domain. You can have a 0 in the numerator of a function. It's not a problem. It's just 0. As long as the denominator is not 0. Okay? How do we feel? We're going to practice more, don't worry. All right, next example, 3. F of x equals the square root of x minus 2. So square root, we don't write the index typically, but what's sitting here is a 2, which is even, okay? So now you go, I want to make sure that the radicand, the stuff underneath the radical sign, is not negative. What's another way of saying not negative in math? Greater than or equal to 0. So you just take exactly what you see underneath here and you set it greater than or equal to 0. From here, you just solve this inequality and boom, there's your domain. So if I add 2 to both sides, then I get x is greater than or equal to 2. And that's really all there is to it. So how to write this out in set builder or interval notation? Set builder, there isn't much else to do. You just declare your variable x such that x is greater than or equal to 2. That's all there is to it. In interval notation, it would be bracket, since we're including 2, all the way to positive infinity. All right, and then if you're struggling going back and forth between set builder and interval notation, I actually have a video. I'll link it in the description should you need to review that. Okay, Good? All right, now look at the next one. It's ever so barely different. G of x equals 1 over the square root of x minus 2. So in this scenario, we have two things to worry about because I have variables in the denominator, and that means I don't want the denominator to be 0. I also have a radical with an even index, so what's underneath has to be greater than 0. Notice I'm not saying greater than or equal to 0 because this time I can't have the denominator equal 0. It would make the function undefined. So in this case, there's really just one little thing that you do different to find the domain. You just set x minus 2 strictly greater than 0, not equal to. And then that'll take care of both issues that we have. That'll make sure that the radicand isn't negative. That way the square root will be a real number. And then it also will make sure, since I didn't put inclusive, I didn't put equals to, that the denominator is not 0. That's it. See the difference? Equals 2 here because this was not in the denominator. Don't put the equals here because this is in the denominator. And then you solve and you just get x is greater than 2. So in set builder, you would write domain is all x's such that x is greater than 2. And then in interval notation, all that would change is you'd have parentheses 2 to infinity, like that. Okay, good. You see the difference between the two? Oh, fabulous. You guys are sharp. Okay, let's continue. H of x equals square root of x minus 2 over x cubed minus 64x. I know I took things to the next level, didn't I? So we have multiple things to consider. First and foremost, I have radical with an even index. It's in the numerator this time. Okay, so that means x minus 2 has to be greater than or equal to 0. So x has to be greater than or equal to 2. That's from the numerator. What else? More things to consider. The denominator. I don't want the denominator to be 0. So I don't want x cubed minus 64x equaling 0. This cannot happen. Now let's solve for x. First factor out an x, and then you have x squared minus 64. I don't want that to be 0. X squared minus 64 factors more. It's a difference of squares, so it factors into x plus 8, x minus 8. And then now using the zero product property, I get that x can't be 0, x can't be 8, and x cannot be negative 8. Okay, so I have to see what the overlap or intersection is for all of these domain restrictions. So I've got x has to be greater than or equal to 2, and then x can't be any of these numbers here. And I'm going to graph it. Some people can just look at it and mentally know what's going on, but let me graph it in case it's helpful to you. So say here's 2. I know x has to be greater than or equal to 2, and then x can't be 0. Well, that's not even relevant because if x has to be greater than or equal to 2, already it's taking care of the fact that x can't be 0. So I don't need to list that. X can't be 8. Is that relevant? Yeah, because 8's like right here and we have to skip over it. Okay, so then I should erase this and just have this portion and then this portion. And then what about x can't be negative 8? Well, that's all the way over here. That's not even relevant because I already have the restriction x has to be greater than or equal to 2. So I don't need to even list x can't be negative 8. So what's crucial to state is that x has to be greater than or equal to 2 and x cannot equal positive 8. So I'll show you how to write this out in set builder and interval notation. Set builder, you would say domain is x such that, and then you're just going to list these two conditions here. Separate them with the comma. X is greater than or equal to 2 and x can't equal 8. You can put the word and in there if you want, or just leave it like that. In interval notation, use the graph. It would go from 2 to 8, parentheses on the 8, because we can't equal 8, union 8 to infinity. Okay? And that's it. So that one, we had a lot to think about because we had a radical and we had variables in the denominator. Nice. Oh, I got more, don't you worry. Here we go. Number 6, f of x equals the cube root of x minus 2. So again, we have a radical, but the index here is 3, and 3 is odd. And there are no restrictions on taking odd roots for negative numbers. You'll still get a negative real number as the result. So we don't have to worry about restricting anything. If there's no restrictions, then the domain is all real numbers. Or we can write it in interval notation. If this was a different number, if it was a 4, a 6, or there was no number, which means it's a 2, then we have to make sure the radicand's positive. But if it's odd, everybody's good to go. Don't sweat it, all real numbers, okay? Now, look at 7, just a wee bit different. Same odd index, it's just now this radical is in the denominator. So almost everybody's good to go. I just know in the denominator we can't have any zeros. So I don't want my denominator to equal 0. So solving for x here, if I raise both sides, I cube both sides, right? I'm still going to have 0. So that just means x minus 2 can't be 0. So x can't equal 2. That's the only restriction. So then my domain is going to be all x's such that x can't equal 2. Or in interval notation, it would go negative infinity to 2, union 2 to infinity. Beautiful. Are you guys getting the hang of it a little bit? Okay. Now let's talk about some logarithms. F of x equals log of x plus 3. This is a common log. The base is 10. When we don't write a base, that's what it is. But that has no bearing on the domain here. You just take the argument, the stuff inside the parentheses, and you set it strictly greater than 0. So not equal to. Why is that? If you'll remember your parent function, y equals log base 10 of x, y equals log x. It goes through 1 comma 0. Vertical asymptote is the y-axis, and it goes up, up, up like this. So the original domain is that x has to be strictly greater than 0, not even equal to. That's why we said it's strictly greater than 0. Okay? Then just solve. So x has to be greater than negative 3. And then you're done. So you just say my domain is x such that x is greater than negative 3. Or in interval notation, since it's not including negative 3, then you do parentheses from negative 3 to infinity. Good job. Look, you guys. You just needed a breakdown, right? Okay. Now let's do a few spicier ones with the logarithms. G of x equals natural log of 1 minus x squared. So again, I want the argument 1 minus x squared to be greater than 0. Now, inequalities are more tricky to solve than equations. If they're not linear, so the one we just did was linear. Look, look, look. You see how when we were solving this guy, it just was x to the first? You could pretty much solve it as an equation. You just know you have to flip the direction of the inequality sign when you multiply or divide by negative. But when you have x squared, or like over here, we're going to do a rational expression, things are a lot more involved. You can't just treat it like an equation. So let me show you a couple different techniques. For this first one, I'm going to ask you to graph, just rough sketch, the function 1 minus x squared. Because basically this is saying when is 1 minus x squared greater than 0 or above the x-axis. So y equals 1 minus x squared. Hopefully you remember, it's a parabola. Y equals x squared is a parabola. This one's opening down, and it's been shifted up 1 unit because of the 1 there. So parabola opening down, shifted up 1 unit. Here it is. And so the solution to the inequality would be all the x values where this parabola is above the x-axis. And that's all here, where the parabola is above the x-axis. So that happens on the interval from -1 to 1. Or in set builder notation, you would say x is less than 1 and greater than -1. And that's our domain. That's it. But don't solve this the way you would solve an equation. You can't move the x over to the other side and then take the square root. No, that's not allowed, okay? On occasion, you'll do some things with inequalities maybe a little later in your math career, but you have to proceed with caution. So I think graphing is a nice, safe way to do it. Okay, another option to graphing is you can test intervals on a number line. So I'm going to show you that right now with example 10. So here we have h of x equals natural log of 1 plus x over 1 minus x. So I want to make sure that the argument is strictly greater than 0. And no, you're not allowed to clear out the denominator and multiply both sides by 1 minus x. In an inequality, that's a no-no. Only in an equation, that's okay. I have a whole video on how to solve rational inequalities. So if you're rusty on this, probably go check it out. I'm just going to show you like a quick little recap right now as we work through this problem. So what you do is, in order to see where this whole thing's greater than 0, make a number line. And on the number line, I want you to list everywhere the numerator is 0 and everywhere the denominator is 0. So the numerator would be 0 if x is -1. And the denominator would be 0 if x is +1. And now we've broken up our number line into 3 intervals. First one is from -infinity to -1. The next one is from -1 to 1. And the last one is from 1 to infinity. And notice I put parentheses on all of these intervals because my inequality is strictly greater than 0, not greater than or equal to 0. And then what I'm going to do next is pick a representative value from each of these intervals, substitute it in for x, and determine whether this expression is positive or negative on each of these intervals to find the domain. So I'll show you what to do. For example, pick somebody between -infinity and -1. How about -2? So if I substitute in -2 for x, in the numerator, 1 plus -2, that's negative. If I substitute in -2 for x in the denominator, 1 minus -2, that would be positive. A negative divided by a positive gives me something that's negative. Well, are negative numbers greater than 0? No, they are not. So then that means this interval is not part of the domain. Good. Now let's repeat the process. So next interval, between -1 and 1, I would choose to test with maybe x equals 0. That sounds nice. 1 plus 0, that would be positive. 1 minus 0, that's also positive. A positive divided by a positive is positive. So this interval is part of my domain. That satisfies the inequality. Positive numbers are greater than 0. Last interval from 1 to infinity, you could do 7, 49, 2. So numerator is positive, denominator is negative. So everything's negative on this interval. That's not going to be part of the domain. So there we go. Here's my domain from -1 to 1. Or again, if you want to write it in set builder, you'd say x such that -1 is less than x is less than 1 and not equal to. Don't put the equals to signs on the logarithms. Okay, good. I wanted to box it and I had no space, so I tried moving it. Here we go. Better. All right, I think the last kind of function that I talked about was inverse trig function, arc sine or arc cosine. We're not going to deal with the rest in this video. So whenever you have arc sine or arc cosine, remember that the argument has to be between 1 and -1 inclusive. So you just set 2x plus 3 less than or equal to 1, greater than or equal to -1. And then solve for x. So when you have this inequality, what you're going to do is first subtract 3 everywhere. And then we have here negative 4 is less than or equal to 2x is less than or equal to negative 2. And then divide by 2, so x is less than or equal to negative 1 and greater than or equal to negative 2. Now, this is ready to go. If you just want to put it in set builder, see? Don't have to rewrite anything. Boom. In interval notation, brackets, right? Between negative 2 and 1. Okay, very good. I have a couple more, a little more spicy, and then we'll get into the calculus. So h of x equals 1 over the 4th root of x squared minus 5x. So I'm noticing I have variables in the denominator, and I also have a radical with an even index. So normally you would just take x squared minus 5x and make sure it's greater than or equal to 0, but since it's in the denominator, I'm just going to set it strictly greater than 0. If this was in the numerator, not the denominator, then I would put the equal sign here. But because it's in the denominator, I don't want it to equal 0. Okay, you could graph this parabola, or we could factor and do the number line and test the signs like we did in the last problem. I think that's a better move. So I can factor out an x, and then you have x minus 5 as your other factor. This needs to be greater than 0. And then again, we're going to make a number line, list the zeros from the left-hand side on the number line. So 0 and positive 5. And then we have 3 intervals here, negative infinity to 0, 0 to 5, and 5 to infinity. And just like in example number 10, you just pick a representative value and test the sign. So say I pick x equals negative 1, that would be negative. Negative 1 minus 5 is also negative. Negative times a negative is positive, right? Very good. Say you pick over here x equals positive 1, positive, negative, positive times a negative is negative. And then say I pick something like 6, positive, positive. It doesn't matter what you pick. Just don't pick the endpoints. And keep in mind, I want the intervals where it's positive because that satisfies the inequality, that it's greater than 0. So my domain consists of these 2 intervals. So you would list them out and put a U between them to show that they're joined together. That's my domain. If you want to write it in set builder, you totally can. It's all x's such that x is less than 0, and then you would write the word or x is greater than 5. Okay. How are we doing? Let's try one that we haven't done something similar yet. G of x equals the square root of 2 minus the square root of x. Ooh, okay. So first things first, I notice I just have square root of x. That means for sure x has to be greater than or equal to 0. Ignoring all this other stuff, if I have square root of x, this x has to be greater than or equal to 0. Now, on a larger scale, I have another radical. Yes? So I want you to notice another radical with an even index. So all of this underneath the bigger radical also must be greater than or equal to 0. So also, or and, 2 minus square root of x has to be greater than or equal to 0. So let's try to solve this. Let me move the rad x over to the other side. So 2 has to be greater than or equal to rad x. If it helps you, switch it around. So this is the same thing as x, square root of x is less than or equal to 2. And then we can go ahead, square both sides. So this means x has to be less than or equal to 4. So I have x has to be greater than or equal to 0, and x has to be less than or equal to 4. Also, or and, means I'm looking for the overlap of these 2 inequalities. Overlap of these 2. Let's graph them. Here's 0, here's 4. x has to be greater than or equal to 0. So from here this way. And at the same time, it needs to be less than or equal to 4. So where's the overlap? Where's the overlap? Right here. The overlap is from 0 to 4 with brackets, So that's your domain and interval notation. In set builder, you would say all x's such that 0 is less than or equal to x is less than or equal to 4. So the key is these two inequalities have to be simultaneously satisfied. The word and also means we're looking for the overlap. Okay, you don't have to graph it, but it just usually helps in case you can't quite identify where the correct overlap is. Let's try another one where we have to think like this. I thought that was a fun one. G of t equals the square root of 3 minus t minus the square root of 2 plus t. So again, we have to figure out where 3 minus t is greater than or equal to 0 and where 2 plus t is greater than or equal to 0. Why don't you pause the video, try this one on your own, see if you can solve each of the inequalities and then find the overlap, okay? Did you guys pause it? I hope you did. Okay, this is the same as 3 is greater than or equal to t, or if you want to write instead, t is less than or equal to 3, and t has to be greater than or equal to -2. You don't have to graph it, but if it helps, by all means, do so. Here's -2, here's 3. And you guys, when you graph, only put stuff that's relevant. You know what I mean? Like, I'm not sitting here all day going, -1, 0, 1, 2. You don't need it. You just need these guys on here. Sometimes you do a little too much and then you make math more stressful than it needs to be. Okay. Anyways, t is less than or equal to 3. So including 3, less than or equal to, and t is greater than or equal to -2 here, this way. Where's the overlap? Again, in the middle. So cute. So from -2 to 3, that's the overlap. This is interval notation. Should you want to write set builder, x such that -2 less than or equal to x less than or equal to 3. Boom. Okay, I have one more, and then we'll do some calculus applications that you'll see in the beginning of your calculus class. F of x equals x plus 1 over 1 plus 1 over x plus 1. Ooh, so this is a complex rational expression or function. We need to simplify it. But before I start simplifying, let me list the first obvious restriction on the domain, because I have a lot of variables in the denominator. But inside this like baby fraction in the denominator, I already can see, ooh, x plus 1. I don't want x plus 1 to equal 0. So x can't be -1. Now, I already did a video going over how to simplify complex expressions. And I'm going to go with method 1 and multiply everything by the LCD of all the minor denominators, which is x plus 1. So then in the numerator, I'm not going to FOIL it out. We don't need to. We'll just have x plus 1 quantity squared. But then be careful, this x plus 1 distributes. So then you're going to have x plus 1, you just have 1 times x plus 1, plus, and then over here, notice, cancel, I just have another 1. So this simplifies to x plus 1 squared over x plus 2. Huh, that's interesting. Because now look at the denominator. I don't want that to be 0. So x can't be -2 as well. So here's the interesting thing. If you just simplified right away and didn't write out that x can't equal -1, you would have lost this first restriction because it's not obvious anymore now that it's simplified. But since our function originally appeared like this, you know, this is how it lives in the wild before we tamed it, you still have to consider the fact that x can't be -1. So both have to be listed. Yes, we're going to list this restriction and this restriction. That's a complete correct final answer. Set builder's the best way to do it, right? When you just have like a couple restrictions to list, it's easy to go x such that x can't be -1 or -2. Interval notation, we could do it. You'd go -infinity to -2, union -2 to -1, union -1 to infinity. Just not as efficient, I feel, but up to you. And then, you know, in calc, you do interval notation so much more than set builder a lot of the time, so it's good to practice. Okay, so why is finding the domain of a function important? Pretty much your whole calculus career, before you start finding derivatives, critical values, and you'll learn all of this, you need to identify the domain of a function. One of the first situations where it comes up is when you're studying continuity. And we have a very beautiful theorem. Because remember, continuity, there's a 3-part definition. If you need a video lecture on continuity, I'll link it in the description. But we don't need to check that 3-part definition thanks to this theorem here, provided our function falls into one of the following categories. If our function is a polynomial, a rational function, a root function, trig, inverse trig, exponential, logarithmic, then it's continuous on its domain. So you don't need to check the 3-part definition of continuity. Rather, to find where the function is continuous, you just need to identify it and state its domain. Do you remember the 3-part definition of continuity? So I'll write it out for you. So I'll just say f of x is continuous at x equals a if all of the following are satisfied. First, f of a exists or is defined. Second, the limit as x approaches a of f of x exists, and it's a finite limit. And then the third thing is that step 1 equals step 2, namely that the limit as x approaches a of f of x equals f of a. And you should be able to write this definition out on your own, okay? However, we don't need to use it, no, we don't, if we can say our function is any one of these, okay? And then you just identify the domain of the function and you move on with your life. Very, very helpful, very efficient. This list looks so exhaustive. You're probably like, I simply cannot think of a function that is not on this list. And the big one that's going to come up are piecewise functions. Piecewise functions are not on this list because piecewise functions are these functions pasted together. And so you always need to investigate where the domain splits or where the piecewise function switches how it's defined. In that case, yes, by all means, you got to bust out this 3-part definition. And I have a whole video investigating continuity for piecewise functions. I'll link it as well. But in this case, we're just going to practice doing the theorem or applying the theorem. So we'll identify which kind of function it is. We'll say which one from the list, and then we'll find the domain. And then we'll say where it's continuous. Okay, here we go. Determine where each of the following functions is continuous. So here's f of x. Right away I go, okay, this is a rational function. So now I need to figure out what its domain is because rational functions are on the list. Well, I know I don't want the denominator to be 0. So that means x squared can't be -1. But that's not going to happen anyway, right? There's no real number that I could square and get -1. So there's no restrictions. So that means the domain of this function is all real numbers. So where is it continuous? It's continuous on its domain on all real numbers. The answer for the domain and where it's continuous will be the same if it's one of these kinds of functions. Okay, that was it. They're not all going to be this easy, but they are all going to be super fun, I think. Here we go. Ooh, g of x equals cube root of x minus 2 over x cubed minus 2. What kind of function is g of x? Well, it's a combo, right? It's multiple functions from the list, but we're good. It's a combo of a radical function and, you know, we've got variables in the denominator. It's a rational function too. So we have a few things to keep in mind. Okay, radical function, the index is 3, which is odd. So I actually have no restrictions to worry about here. X minus 2 can be positive, negative, 0, we're good. The only issue is I don't want the denominator to be 0. So I don't want x cubed minus 2 to be 0. So x cubed can't be 2. So x cannot be the cube root of 2, whatever it is. So that's where the function is continuous, everywhere except the cube root of 2. So you could say continuous for all x except x equals cube root of 2. Okay, that's good enough. We're not really writing a formal domain, but if you want to write it in, you know, as a set or as an interval, that's fine too. Okay, moving on. F of t equals e raised to the sine t over 2 plus cosine pi t. So this is a combo of a lot of things. Rational, exponential, because we have e raised to the sine t, trig. But those are all on the list. We're good. Like, you guys, basically, as long as it's not a piecewise function, it's on the list. That's the cool part about it. So no restrictions on domain for exponential function. Their domains are all real numbers. Only issue is I don't want this denominator to be 0. So 2 plus cosine pi t can't be 0. That means cosine pi t can't be negative 2. But do you remember what the graph of cosine looks like? You do? Oh, good. I'm so excited. So here's xy. Cosine is bounded between 1 and negative 1. Here's like a rough graph of cosine. Boom, boom. Here's 1. Here's negative 1. And cosine is just trapped in here. Trapped like a rat. So could cosine ever be negative 2? No, certainly not. That's all the way down here. So this is not possible, which means there's no restrictions. So again, the domain of f is all real numbers, and it's continuous on all real numbers. No restrictions. Everybody's good to go. Okay, nice, huh? I feel so like positive when all real numbers are good to go. I'm like, oh, fabulous for us. Okay, next one. H of x equals the square root of 1 plus 1 over x. So what is this? This is a combo of a radical and rational function, right? Because we've got variables in the denominator. It's like a composition of the two. Okay, well, what do I know? When I have a radical sign, index is even, the radicand has to be greater than or equal to 0. How do I solve this inequality? Don't even think about moving the 1 over to the other side. Nope. We have to, this is a rational inequality. We're going to get a common denominator, list the zeros on the number line, test the sign. So common denominator is x. This is going to be x over x. So then I have x plus 1 over x is greater than or equal to 0. Let's make our number line. Remember, you put the zeros from the numerator and denominator on there. So negative 1 and 0. Now the intervals are going to go from negative infinity to negative 1. I put a bracket here because it could equal 0. And if x is negative 1, the numerator is 0. That's fine. Next interval goes from negative 1 to 0, but parentheses on 0. Why? Because this was a 0 from the denominator, and we can't actually equal 0 because then this expression would be undefined. So don't include 0. Negative 1 is fine. That was a 0 from the numerator. And then last interval is from 0 to infinity. Okay, then just test a value in each. You could use negative 2, negative 0.5, 1. I tested them already. Positive, negative, positive. Which one works? The ones where it's positive, because we want this expression greater than or equal to 0. So the function is continuous on its domain, which is from negative infinity to negative 1, union 0 to infinity. You really wouldn't need to write this in Set Builder, but should you just want to know how to do it, you would say x such that x is less than or equal to negative 1 or x is greater than 0. But like I said earlier, most of the time in calc, you're just doing interval notation. Okay, example 5. G of t equals cosine inverse of e to the t minus 1. So this is an inverse trig function composed with also exponential function, e to the t, but those are all on the list. So I just have to find the domain of g, and that's where it's continuous. Take the argument on cosine inverse, and it has to be bounded between 1 and negative 1. Let me try to solve for t. So adding 1 throughout the inequality, I'll get 0 is less than or equal to e to the t is less than or equal to 2. Now, do you remember the graph of e to the t? I'll say this is t. And then e to the t goes through 0, 1, exponential function. And then remember, we have horizontal asymptote over here. So it's never negative. Why is that important? Because I can drop this part of the inequality. Saying e to the t has to be greater than or equal to 0 is redundant. It automatically is. So I only need to solve e to the t is less than or equal to 2. Oh, good. Now I'm going to take the natural log of both sides. So then that means natural log of e to the t, which is just t, needs to be less than or equal to natural log of 2. And that's it. So that's the domain of my function. That's where it's continuous. In interval notation, you would say from negative infinity to natural log of 2, or Set Builder t such that t is less than or equal to 2. Make sure you are precise. Like if there's t's here, don't switch to x's. You have to honor the variable of the function. It's like its name, you know. Don't change its name unless it gives you permission. Okay. Example 6. H of x is x times natural log of 1 minus x squared. So this is a combo. I mean, we have x times natural log. So yeah, logarithmic function, kind of a polynomial, all of that stuff mushed together. The x out front isn't doing anything to affect the domain. It can be whatever it wants to be. The only issue is that 1 minus x squared has to be greater than 0. We've done this before. Remember, I had you graph 1 minus x squared. You could also, if you want to factor and test the signs on the number line, that works too. Okay, but you can't take a square root nicely. You have to do it with such caution. I just don't even want to talk about it. Okay, so here's 1 minus x squared. Where is it greater than 0? If x is between 1 and negative 1, or in interval notation, you would write it like that. So that's the domain of the function, and then that's where it is continuous as well. Okay. Are they feeling repetitive? Do you feel professional already? You're like, throw me a function. I can find the domain, no problem now. That is my goal. That was my goal. Ooh, here's another one. Okay, so f of x is square root of 3x minus 2 plus cube root of 2x minus 3. So these are radical functions. I know the first one has an even index because there is nothing written there, which means it's a 2. So I need 3x minus 2 to be greater than or equal to 0. I don't even care about this though, because cube root, that's odd. X can be anything. If this is negative, we have no issue. So just ignore it. That means 3x has to be greater than or equal to 2. So x has to be greater than or equal to 2/3. So that's the domain of this function. That's where it's continuous. I would put it in interval notation. It's continuous from 2/3 to infinity. Beautiful. Okay. How many more do I have? Let me tell you. I have 3 more. Okay. I just wanted to give you enough of a variety so you feel prepared. I hated it when I didn't have enough examples in my class to do my homework or for any scenario that would pop up. Okay, h of t equals cosine of t squared over 1 minus e to the t. So what is h? It's like a combo. Rational function, trig function, exponential function. You've even got like that t squared. Technically, we could say it's a little bit of a polynomial. It's just a mishmash of all of these, but it's all good. The theorem still applies. Do I care about cosine? No, it's not inverse cosine. So there's no restrictions on t squared, okay? I do care about this denominator. I just want to make sure it's never equal to 0. So 1 minus e to the t can't be 0. That means e to the t can't be 1. How would that happen? If t is 0. You could take the natural log of both sides if you want, or maybe you can just think about it, right? Like e raised to what power gives me 1? It's only if t is 0. So that's the only restriction on my domain. So that's the only place where h is not continuous. So h is continuous on negative infinity to 0, union 0 to infinity. And that's your answer. Beautiful. Okay, 2 more. F of x equals x squared over the square root of x to the 4th plus 2. So let's identify it. It's a rational function, radical, technically kind of like a polynomial. When I say rational, like technically a rational function is a ratio of 2 polynomials, but rational in the sense that we have a ratio of 2 functions, okay? Let's see, x squared, don't care about him. The radical, yeah, I want to make sure this is an even index, that the radicand, the stuff underneath, is not negative. So x to the 4th plus 2 must be strictly greater than 0. I'm not even going to put equals to because it's in the denominator. That means x to the 4th has to be greater than negative 2. But you know what, you guys? That's always true, right? You can't raise something to the 4th and get a negative number if you started with a real number. So this is always true. No restrictions. So that means the domain is all real numbers. So f is continuous on all real numbers. Negative infinity to infinity. Okay, last one, 10. G of v equals 3v minus 1 over v squared plus 2v minus 15. So g is a good old rational function. I just don't want this denominator to be 0, right? That would be problematic. Can you solve? Can you factor? V plus 5, v minus 3, right? So that means v can't be negative 5 or positive 3. Otherwise, g is continuous everywhere. So g is continuous on, let's write it in interval notation, negative infinity to negative 5, union negative 5 to 3, union 3 to infinity. Woo, that was the grand finale. I hope you enjoyed that last problem. You know, it's gonna make me so mad that it didn't straighten up. I think there was one other crooked one in the video. Okay, much better. I hope this was helpful. I hope you feel better about finding domains. And you know, this channel is called Math with Professor V because I am a professor full-time at a community college here in the US. And my students, when I teach Calculus 1, always forget how to find the domain of a function. And I think it's because it's never taught all at once. When you learn new kinds of functions in pre-calc, we go over how to find their domain, but we don't do a nice comprehensive review at the end and go, okay, here's all the things that we've learned, here's what to look out for. So that was the purpose of this video, because you just need to know how to tackle it once you've learned all the functions from your pre-calculus course. So I hope you found this helpful. Give the video a thumbs up if you did. Subscribe if you haven't already. Check out the description in case you need full-length video lectures on any of the topics that I went over, because the purpose of this video was just to really hone in and get you guys good at finding domains of functions. And if there's other functions, I take requests from my channel members and those who are on Patreon if you have any particular topic requests. And also follow me on Instagram, TikTok, Math with Professor V. Thank you guys so much for your support, and I wish you all so much success with your math classes. Truly, my mission is to help so many students around the world not struggle as much with their calculus courses in particular. I love you all. I'll be back sooner than later.